I will text the director. No, I told the kids that are helping with the organization that if we start, and there are some, since they are helping with the organization, they can take the seats. Isso aqui é tudo gente que está sem ingresso. Pode começar a liberar para alguns entrarem.
Faltam 20 pessoas.
Pois é, faltam 20 pessoas com ingresso, mas já está na hora de começar. Então vamos priorizar para quem estava aqui na aula. Tá?
Já vai pegar todo mundo dentro da cabine?
Já. Tá. Aqui, pessoal, falei que vocês podem ocupar. Vocês entrando, as cadeiras que já estiverem reservadas, vocês podem ocupar, menos as duas últimas lá. Quando o diretor chegar, as reservadas vai ter lugar para isso, tá?
Pode liberar.
Vai liberando aos poucos. Isso aqui é fila de chegada, ordem de chegada? Então pode ir liberando.
That's a hot mic.
Yes. Yeah, I think they will take care of it.
Não pode sentar?
Aqueles dois ali do cantinho.
Os outros reservados?
Pode.
A gente vai liberar só o que está restante ali e já fechar.
Tá. Você está vendo o professor Luiz Antônio, o professor Luiz Henrique? Ah, estão ali. Não, é só porque eu estava na dúvida de onde que eles estão. Ah, professor!
Boa.
Que bom que você veio. Deixa eu apresentar.
Não dava por causa da barulhada, eu não ia.
Ah, tá. This is Patricia's father. We were talking a lot about him yesterday.
I was supposed to go there, but I have a very bad hearing stuff. And with lot of noise, I thought I was able to talk to you.
Maybe another time. I'll be back.
Yeah, but my daughter told me fantastic.
We had
So I
lots
said,
of fun.
Well, we'll talk some more fantastic stuff today. So please.
Yeah, okay.
Gente, vamos nos ajeitando aí para a gente tentar começar sem muito atraso. Então, vamos ocupando aí, vamos... Enquanto vocês se acomodam, eu vou fazer uma pequena introdução aqui, só porque alguns de vocês me perguntaram como assim James Green veio para o FMG, né? Como que a gente conseguiu essa pessoa fantástica para estar aqui? Eu tive o prazer de trabalhar na Universidade do Espaço, Universidade Internacional do Espaço, em 2021, 2022, 2023. Na edição de 2022, que foi em Portugal, eu tive a oportunidade de ficar como assistente do Jim por um pouco mais de um mês, e eu pude conhecer melhor ele, o trabalho dele, e eu achei tudo incrível. Eu tive a oportunidade de ver várias palestras, várias aulas dele. E eu ficava muito pensando, tipo assim, que eu ia ficar muito emocionada se eu tivesse a oportunidade de que vocês tivessem um pouco disso que eu tive, né? E aí, no ano seguinte, que foi em São José dos Campos, eu trabalhei mais diretamente com o Jim no que a gente chama de TP, Team Project. Eu estava orientando junto com ele o trabalho do Team Project, com ele e com o Jacob Cohen, que é também da NASA. E aprendi demais, gente. Foram meses incríveis a gente preparando no virtual. E foram semanas incríveis trabalhando com ele no presencial, todo dia nisso. E a única coisa que eu conseguia pensar é que eu queria muito que vocês tivessem isso que eu tive. Eu queria muito que eu, com 20 anos, tivesse essa oportunidade. Eu pensei, um dia eu vou ter a oportunidade de levar o Jim. E aí, essa semana, ele estava aqui no Brasil para um congresso de agronomia espacial em São José dos Campos. E eu perguntei para ele, tipo, Jim, você tem um tempinho para conversar comigo? Videoconferência? Eu queria que ele visse minha cara de pidona, né? E aí eu virei para ele e falei assim, poxa, você já vai estar aqui no Brasil, é só 1 horinha de voo, vem para BH ver meus alunos. E ele, sem hesitar, claro, eu vou. A minha volta é na sexta-feira, eu vou mudar meu voo para o sábado para estar com seus alunos. Então, este homem mudou o voo dele em um dia para estar aqui com a gente. Eu fico muito emocionada de saber que tem alguém tão importante que fez questão de estar aqui com a gente. Bom, então, a gente trabalhou, então, eu sempre tenho contato com ele, né? A gente sempre conversa coisas muito interessantes, e eu estou muito feliz de trazer para vocês a oportunidade de ouvir. Vocês vão ver que a palestra dele é incrível. Estou muito emocionada que vocês vão poder usufruir disso. Gostaria de agradecer o apoio da diretoria, principalmente o diretor, o professor Henrique, que saiu procurando auditório para a gente, conversando com 1000 pessoas, corre atrás disso, e se ele precisa de alguma coisa, fez acontecer. Eu queria agradecer muito também a professora Juliana, o professor Luiz Henrique, que sempre apoiam, eu apareço com as ideias, eles apoiam. E não foi diferente, eles apoiaram dessa vez, né? Jim pediu para fazer uma introdução bem breve, eu falei com ele que eu ia rapidinho apresentar isso aqui antes. Que ele virou para mim e falou, não gasta 5 minutos me apresentando, não, que são 5 minutos a menos para eu falar com eles. Então, eu falei com ele que eu ia falar rapidinho. Então, Jim trabalhou na NASA por 42 anos. Ele... Ai, perdão, gente. O DA da Engenharia e a Aero Júnior me perdoam. Muito obrigada ao DA e a Aero Júnior, gente. Me perdoem. Então, o Jim trabalhou na NASA por 42 anos como cientista-chefe. E I forgot to thank the students, the kids, and that's the reason I had to go back. Ele trabalhou na NASA por 42 anos, ele foi cientista-chefe de dezenas de missões planetárias, e vocês vão ver que ele fala disso com tanta paixão que vocês vão sair daqui todo mundo com vontade de ir para a NASA, ou melhor ainda, de trabalhar no setor espacial no Brasil, porque a gente precisa de vocês. Thank you, Jim. I'm sorry for taking longer than I promised.
Yes. Thank you. Thank you very much. Thank you. She promised me it would be a very short, couple-sentence introduction, which is what I wanted. And I'd hate to see the long version. So, unfortunately, I cannot speak Portuguese. My languages are Fortran, C++. I have lost my ability to speak Spanish. German, which I took in college, is also faded from view. So I hope I will talk slow enough that you will be able to get the idea of what we're going to talk about today, which is very exciting. And feel free to take pictures. I'm delighted you can post anything you like about what's going on and things that you might learn today that you did not know. I want to thank very, very much Maria Cecilia for inviting me here. I do listen to what she says, and so students, please do the same. I also would like to thank very much the university that is providing the facilities and helping make this beautiful venue happen. I took a wonderful overview of the university today, and I'm so impressed, and I'm just delighted to be here to talk about one of my absolute favorite subjects, planetary science. So over the last 65 years, NASA has sent spacecraft into the solar system. In fact, we have several spacecraft that are now leaving the gravitational influence of the sun and are starting to taste the winds of other stars. These, of course, are the Voyager spacecraft. We have another one right behind them, which is the New Horizons spacecraft that will also leave the gravitational bounds of the sun, punch through the heliosphere, which is the magnetic field that the sun puts out that is pulled and pushed as it moves through various clouds of materials, gets hammered with cosmic rays, and protects the inner solar system such that we can have life on this planet. So what's happened in the last 65 years is that NASA has completed our initial survey of the solar system. And that has revealed a number of unbelievable things that are going on. And I don't have time to tell you all those, but I'm going to try to pick out certain things as we go through each and every one of the planets in the solar system. This, of course, is Mercury. It's very close to the sun. It orbits the sun in 88 days. It is nearly tidally locked, but not quite. One day on Mercury is 59 Earth days, but as you get closer to large bodies, they have a tendency to lock your orbit such that one face of that object will point to the larger mass. And we call that tidal locking. This is a very important phenomenon because as we learn more about our own solar system and apply what we know to other solar systems, we then can see what planets would be tidally locked, where one faces the heat of that sun, and on the night side it stays incredibly cold, and that doesn't make it a very habitable world. So the more we learn about our own solar system, the more we can apply that knowledge to looking for life on planets orbiting other stars. When I graduated at the University of Iowa, I had an astronomy degree, a physics degree, master's, and a space physics as a PhD. And there were many things that we thought we knew. For instance, there was no hope of seeing another planet around another star. Just forget it. Fortunately, many scientists didn't believe that mantra and worked hard to figure out how to do that. And we now know, as we find other planets orbiting other stars all over our Milky Way, that there are more planets than there are stars in our galaxy. And now, what we learn about our own planets is important, because are those planets like Mercury, Venus, Earth, Mars? What are they like? And so we're going to use our planets as that Rosetta Stone to interpret what we see around other stars, their solar systems, their planets, their debris, their comets, all the things that we have, they have too. Well, Mercury is very close to the sun. It's very hot. It's nearly tidally locked. It looks like the moon. Now, this is observations from the Messenger spacecraft that orbited Mercury for many years, getting wonderful high-resolution imaging of the entire planet. This planet is bigger than the moon, but smaller than Mars, much smaller than the Earth. You can understand that because as planets form, they gather material as they orbit, and if your orbit is close to the sun, there's only so much material you can accrete. So we would expect the planets that are closest to the sun to be the smaller ones. But Mercury has other secrets. The secret of it looking like the moon is exciting. It has no atmosphere. It's too close to the sun. It's too small to have hung on to that atmosphere very long. The solar wind, which is the outgassing of the sun exhales all the time in all directions, has an enormous effect on atmospheres of planets. And Mercury is sitting in the hot part of the solar atmosphere because it's the closest planet. And therefore, the atmosphere of this planet is gone. But here's one of the most exciting discoveries of Mercury from Messenger. This is from the Messenger spacecraft, which orbited Mercury even over the poles. This is a polar view of the planet, and we color in red in this image where we see the signal of water. Now that is not liquid water, it's frozen water, but this was a shocker. How could that be? We're way too close to have water on these planets, this one in particular, close to the sun. But we find that in these craters, there's a lot of frozen water. Okay? We now realize that when we do an image movie, as I just showed you of Mercury, and how the sun shines on the planet, even though its axis has a spinning and it's very slow, the North and the South Pole has places where the sun does not shine. And so as comets hit this planet, as asteroids, which we know asteroids have actually plenty of frozen water in them. Didn't know that till we went there and found that material, brought that material back to Earth and have analyzed it from a number of asteroids, that those things that bombard Mercury over billions of years leave the water behind. And the sun, since it doesn't shine in these areas, doesn't allow it to be evaporated or disassociated. And so it stays together as a frozen solid. Now this is quite exciting. And I'll tell you why a little later on. So our next planet is Venus. Venus also is a pretty exciting planet. It is about the size of the Earth, just slightly smaller. So it's in an orbit that's about 75% of the distance to the sun as we are, all right? And yet it swept up enough material to be about the size of our Earth. So as we study Venus, we realize since we're further away, maybe we should actually be bigger. And so why are we just a little bit bigger than Venus? Why aren't we much more bigger than Venus? And we've understood that secret too. And I'll tell you that when we get to Jupiter. But what's happening at Venus is that it has a very extensive cloud cover. As our spacecraft have orbited this fabulous planet, we cannot see the surface in our optical instruments. Some of the infrared instruments can see nearly down to the surface. There are a couple wavelengths we might actually get down to the surface under certain circumstances. But there's one way we can reveal the secret of Venus's surface, and that's with radar. So we launched a mission called Magellan. It orbited Venus, and its radar was used to shine through the clouds, bouncing off the surface, having that radar signal come back, be received by Magellan, and timed so that we can get the topography, how the highs and the lows, and put a map together of Venus. So I'm going to fly a movie. Here is Venus as we peer through the clouds. And as we do that, we see the surface features are quite varied. There's highs and lows. In fact, the surfaces in and around these high areas look like molten rock. These look like absolute volcanoes. And there's not one or two. There are many. And even the topography between these high hills seem to indicate that that rock has melted, flowed onto the surface in the past, and solidified. And so this is also a tremendous shock. Why is Venus so volcanic? Now we realize that in the past, with all this volcanic activity, what comes out of volcanoes are a tremendous amount of dust, but also a lot of gases. Water vapor, phosphine, sulfur, many different types of material in gaseous form is emitted and builds up an atmosphere on Venus. And now we know the atmosphere on Venus, because we've measured it, is really thick. Here on Earth, we have 14 pounds of atmosphere above us pushing us down. Okay, and we call that one atmosphere. The surface of Venus would be unbearable. It is 90 atmospheres in pressure. Now we can actually feel what that pressure is like by going into the ocean and go more than 1,000 meters to get about 90 atmospheres of pressure. All right? It's crushing depth. And this is why it's been very hard to land anything on the surface of Venus. In fact, the Soviet Union, this was before it became Russia, launched probes in the 70s that actually made it to the ground and lasted for tens of minutes, only to be crushed later on. And we've measured the temperature. The high pressure means a high temperature. It's so hot on the surface of Venus, it would melt lead. It would melt lead. So Venus is a very different planet. So we have revealed the secret of what's below the clouds. We have revealed an understanding of how the atmosphere has become so thick by the constant volcanic activity that seems to go on. And Venus doesn't spin very fast. And it's also nearly tidally locked. And it's not that far away from us. And so these are things that we must know when we look out into space and see other planets the size of Venus, whether they're Venus-like or they're Earth-like. Now, we have had trouble figuring out what the history of Venus is, but we've made a couple really spectacular measurements only a handful of years ago. And this measurement, some may know, we're not going to have a quiz on this. It's called the D to H ratio. Okay? So for the chemists, deuterium to hydrogen, we have deuterium to hydrogen ratio here on Earth. We can go out and go in the ocean, bring back a vial of water, and we can count all the hydrogen linked to oxygen and all the deuterium linked to oxygen. And deuterium is a hydrogen-like atom that has a proton and a neutron stuck together. And there's a certain ratio, certain D to H. Now, that is also called heavy water. If your water, H2O, actually where one of the H or both of the H's are deuterium, it's actually heavier than the hydrogen. And so in an atmosphere of water vapor, the heavier water will lie low. All right? And so when we measured the D to H ratio on Venus, because it does have some water vapor, we were in for a really big surprise. It has a huge amount of deuterium. So if that ratio is the same as Earth, that means, where did that go? Where did that water go? All right? So we now have done some modeling, and how we do that modeling is we take the surface of Venus that we determined from Magellan. Here's what it looks like. This is colored in altitude. The red and the whites are the highlands, and the blues are the lowlands, and the greens and the yellows are the ancient shoreline. All right? And then we take all the missing water that we think should be there, and we put it on this planet. And then we let our models evolve it into its future, and we can get it to look like the Venus of today. Now, this is really exciting, because now we have a better idea as to how Venus evolved. And so what we see is we see the intense heat from the sun heating what we call the subsolar point right on top of the planet, produces a huge column of water vapor, an enormous number of clouds, right where the sun shines, and that helps reflect the light. And so now we recognize that the cloud structure on Venus in this manner, which is concentrated on the day side, this is before we have what we have today, allowed Venus to have its ocean, not for a little bit, but for billions of years. For billions of years. And it's only been recently, it's only been in the last billion years that Venus could no longer withstand the heat of the sun, and that took over, along with the volcanic activity, a process where the water became water vapor, and as the H2O moved, because there's a water cycle, you evaporate it off the ocean, it then moves and then rains, but you can break that cycle if you destroy the water as it's moving, and then the solar wind pulls out the oxygen and the hydrogen, and you break that water cycle, and the rain doesn't happen. And so the ocean whittles away. So 1 billion years ago, this is what Venus looked like. We now recognize that this may have actually been our first habitable planet. All right? But there's no life on the surface today. And we cannot determine if there's any life below the surface, but that's a possibility. Now, Earth is slightly larger than Venus. Our models indicate it should be even larger than it is. And we now have discovered why that's the case. And it has to do with the planet Jupiter. Jupiter, which is an enormous planet, and it is only 4 astronomical units away from us, okay, at its closest, where 1 astronomical unit is the distance from the sun to the Earth, all right? So we're at 1 astronomical unit, and Jupiter has accumulated about 300 times the mass of the Earth, and therefore sucks material its way. So the material that would have made Earth bigger has been sucked away over time by Jupiter, okay? So the Earth, of course, has tons of secrets. If you're an Earth scientist, you revel in so much data to understand what the early atmosphere of the Earth looks like, to understand, you know, when did life start on Earth? You can find it in the rock record. And our rock record indicates that life started about 3.8 billion years ago. But the oldest rocks we have on Earth are 3.9 billion years old. All right? 3.9 billion years old. But what happened to Earth and the moon can tell us how old those 2 objects are. And we have to study that to determine the age of the Earth. And to find the age of the Earth, we actually go to the moon to do that. Why? Because the ancient rock on Earth is gone. Plate tectonics, weathering, all the things that we're used to, has buried that rock and melted it, never to return. So we had an inkling that Earth was going to be older than 3.8 or 3.9 billion years. But when we go to the moon, we can find out what that is. Now the Earth, of course, is teeming with life. And we know there's several things about that we believe are a contributor to that situation. And that's the Earth's magnetic field, the Earth's magnetosphere. That has protected us against violent solar storms with intense solar wind that really rip magnetic fields apart. And if you don't have a magnetic field, it'll rip apart your atmosphere, never to return. So we've been very lucky to have a magnetic field that has kept us relatively safe from the ravages of the solar wind. So as I mentioned, if we wanted to find the age of the Earth, we knew that we had to go to the moon to do it. Why? Because we don't think the moon had plate tectonics. And so we believe the Earth and the moon had similar origins, and we needed to prove that. And we proved many things, and in fact discovered other things by bringing rocky material back from the moon. Okay, so here's the moon. Very familiar at night, you can see it. What's there are the locations of the Apollo landings. And for those that are skeptical, yes, we landed on the moon. I can prove it. Okay, and we brought back about 380 kilograms of rocky material, cores that we took, loose rocks, loose material on the surface, and brought them back into our laboratory and age dated them. And so the age of the moon tells us the age of the Earth. And the composition of the moon is nearly identical to that of the Earth. And so now we believe we understand the story of the Earth and moon and its origin. And it goes like this. About 4.6 billion years ago, that's how old the Earth is, there was a planet, we call it the proto-Earth, at about the location of 1 astronomical unit. But other things were being accreted in that orbit. Another body, about the size of Mars, now Mars is smaller than the Earth, bigger than the moon though, was also accreting. And there was a gravitational fight between the two, and the proto-Earth won, pulled in this other planet. The planetary astronomers call that planet Theia. And Theia crashed into the Earth. And so the material that was made up of Theia and the proto-Earth material mixed, and it was an enormous explosion. There's a location outside the Earth called the Roche limit. And anything in that limit, which is about 3.9 Earth radii away from the center of the Earth, will fall back onto the Earth. Think of Saturn's rings. That material will fall into the planet, all right, over time. So we'll lose the beautiful Saturn rings. So the early proto-Earth had ring systems that looked like that as that material came down, rained on our Earth, and we accumulated that material. That's all inside the Roche limit. Outside the Roche limit, you can accrete another body, and that turned out to be the moon. And so by going to the moon, which, as I mentioned, was created pretty close to the same time the Earth was, we can determine the age of the Earth at about 4.567 billion years old, okay? Older than any of the oldest rocks we can find on Earth. Now, when we look at the moon, we know it's tidally locked. It's close enough to the Earth that over time, as it spins and the Earth pulls on it, and the material that's in this body is not evenly distributed. We think of a body like that and we think that it's just homogeneously, evenly distributed throughout, and that's wrong. There are areas inside the planet that are more massive than other areas, the same depth, but at a different location. Those mass concentrations get attracted to the body that it's rotating, and we yank on it, and eventually this body will become tidally locked. That means we see one surface. We don't see the far side. We only see the near side. And we see huge areas that are darker than the other areas. And we call those areas the mare. And the rocks that we brought back, we can age date them. And we see that that is the younger portion of the moon. And that this rock was lava. It's basaltic rock. Also call that basaltic rock. And so what you're looking when you look at the dark areas on the moon are areas of impacts from huge objects that have ripped huge holes in the crust of the moon, and molten rock poured in it and created, because it brought up material that had more iron, more aluminum, more magnesium in it, a different color look and about it, a different spectral signature, and our eyes integrate that into these dark spots. So we know an enormous things about the moon because of Apollo. But here's where we're going next. We've been to the surface of the moon, mostly in areas that are in low latitudes, but we haven't been to the poles. And so when we look at the moon and we look at the poles, and then as we image the moon over and over and over again, over a period of a month, we can put together this view. This is a view of the South Pole at the moon every day for a month. All right, and so what do you see? Well, you see some areas that maintain a dark, no sunlight can get in, and therefore, what's in them? Well, we know what's in these dark areas. We call these the permanently shadowed craters. And we know, indeed, From Mercury, we see water. And so when we look at these areas, and we're considering landing sites in this particular part for the Artemis program, but when we do the spectral analysis, the blue is water. So the moon actually has a significant amount of water, maybe a million tons of water in the South Pole in these areas. Now, why is water important? Can't find water much in the rest of the moon, but here's a reservoir of water that you can melt, and you can drink it, okay? You can drink this water. Now, here's Earth water, but it might as well be moon water. H2O is H2O, right? Thank you. So that resource we can drink. We can also break it apart into hydrogen and oxygen, and we can breathe the oxygen. We can also break it apart, once again, hydrogen and oxygen, and we can create rocket fuel. So we have an opportunity then in this location to build some permanent bases and use the resources that are trapped in these permanently shadowed areas. So we've uncovered these secrets of the moon, and they've been pretty spectacular. Now for the doubters. Here's high-resolution imaging of the Apollo 12 landing site. And I did this with one of my satellites called the Lunar Reconnaissance Orbiter. If that chair sat on the moon, we could see it from orbit. And so what you're looking at is where we landed, where the astronauts got out, where they walked around. Actually, in this image, went too quick. You can actually see their backpacks as they threw them out and got into the capsule to return home. We deployed instruments on the surface. In fact, there was a spacecraft called Surveyor 3, not very far away, that we walked to and took a look at that. And so these astronauts were all over the place. All over the place. There's Surveyor 3. And we can see their trail. We can see what they did, where they went, what they saw, and we can integrate the images from the surface with the images as we fly over the area. So we're going back to the moon. We've already started the process by building the right kind of rockets and the right kind of capsules. We've launched Artemis 1, which was very successful. There was hardly anything wrong with it, but there were always a few things. And this was an unmanned capsule. We put some dummies in the seat, and we outfitted them with all kinds of experiments. And then we blasted them off the surface. We took this trajectory around the moon. We were gone for a couple weeks. The rocket we've built is called the Space Launch System. It's more powerful than the Saturn V because the Space Launch System also has the ability to take us to Mars. The commercial sector is also building big rockets like Starship that would be a competitor against the SLS, but the SLS is the only one that's working right now, and that's the one we're using. So Artemis 1 was very successful. Artemis 2, early next year, will fly with humans on board. We'll take a trajectory like this and fly beyond the moon and come back. This is very similar to what we did with the Apollo program. We didn't land the Apollo program until Apollo 11. Apollo 8 was the very famous one that went to the moon with astronauts and took the picture of the Earth rising above the horizon. And and that is a well-known picture. So we're gonna pretty much redo that kind of analysis. That seems to work when we do things in step. Our philosophy is, in these linked missions, let's do one miracle at a time, and then once we perfect that, we can build on that. Soon after that, we're looking for Artemis 3. It's much more complicated, and that will get us down to the surface of the moon, into the South Pole, that will allow us to start building capability to remain there for maybe hundreds of years, and build the capabilities to analyze material, to survive, do a variety of other work, even manufacture things. As I look out, I see a lot of phones taking pictures. That's wonderful. Your phone is a wonderful object. It's full of platinum group metals, all right, which are mined in the crust of the earth, only in a few locations. And in the next 50 to 200 years, we won't be mining them anymore because we will have taken them all out of the crust. But there's a lot of platinum group metals up on the moon. So the more we stay there and study what's available, the more we recognize we'll be using other kinds of resources on the moon. And we may even have some manufacturing capability of mining platinum group metals and building things and launching things from the moon. So all kinds of exciting things can happen. The real secret of the moon is this. The moon has made us uncommonly habitable. We are not tidally locked to the sun. The angular momentum that we have, that we lose over time as the moon creeps away from us, has been a wonderful opportunity for life to evolve on this earth, taking advantage of their circadian rhythms, creating tides. The initial idea of humans evolving over time from life that started in the ocean is still a very viable thought, brought to the shore through tides, created by the Earth-Moon interaction, and has allowed this 24-hour day to be a really perfect environment for life to survive on this planet. Thank you, Moon. Now we can go to Mars. So Mars is about 1.5 astronomical units away. Okay, and it's a runt of a planet. Okay? It should be much bigger than the Earth, but it's not. It orbits an area around the sun where there was far more material, which is why it should be bigger. But it's not. And Jupiter has pulled that material away from Mars, making it a smaller object. Now, from my perspective, I am absolutely delighted. And the reason why, even though the Mars is smaller than the Earth, but much larger than the moon, is it enables us to land on the surface, to live and work on the surface, and leave the surface without a huge infrastructure that we have here just to get into space. So the fact that Mars is much smaller is actually going to enable us to put humans down on the surface and live and work on the fabulous planet Mars. We have launched about, not only NASA, but many of the other space agencies, more than 55 missions to Mars. And half of them were successful. And the other half were lost or crashed or flew by and just missed it completely, all right? So getting to Mars has been tough over these last 65 years. But we have managed, with the 26 or so that are tremendously successful, to really get an idea of the history of this planet. And we recognize that Mars was a blue planet just like the Earth 4.5 billion years ago. We had oceans on this planet. Now the ocean is no longer there, but the mineralogy and everything that we see tells us that water has interacted with the rocks, creating new minerals. We can see the atmosphere has been significant enough to allow liquid water to be maintained on the surface. But something happened about 2.5 billion years ago, and that was rapid climate change occurred. Now, as a planetary science, when I say rapid, I'm talking probably about 100 million years. Okay, that's pretty fast. So over that period of time, the climate on Mars tremendously changed. And we know that Mars had a magnetic field. And I'm a magnetospheric physicist. The idea that once Mars lost its magnetic field and the solar wind started to scour the atmosphere is very viable. And so over time, the atmosphere on Mars is much less than that here on Earth. So the atmospheric pressure on the surface of Mars is 7 millibar. The atmospheric pressure on Earth is 1,000 millibar. So in other words, on Mars, the atmospheric pressure is about 1%. And it's mostly carbon dioxide, so you can't breathe that, all right? You'll have to have some sort of spacesuits. So how many saw The Martian? Okay, did you see The Martian? All right. That's the kind of spacesuits we're talking about. Those are surface suits as they walk on the planet. You'll still have to have them until the pressure increases and the temperature increases on Mars. The temperature, the high, is maybe 10 degrees C. The low is minus 100 degrees C. Every day it goes through that cycle. You know, a huge temperature variation on the surface. And that's because primarily of the very thin atmosphere that it has. Well, humans going to Mars are going to start changing the environment, making it easier to live and work outside. We call that process terraforming, okay? And although scientists don't like the idea of terraforming Mars, many of them don't, I've written a couple papers on terraforming Mars, so I've had to turn in my planetary science library card. I'm not too popular with some people. But I have to tell you, in all honesty, we're terraforming the heck out of this planet, and if we show up there, that's going to happen there too. I mean, we have to have oxygen, we have to have food, we have to use the environment, and that means it will have to change. And that's okay. This planet, with the life that's on it, has co-evolved. All right? We affect the geology of this planet, and the geology of this planet has affected us. All right? So we have to think in terms of co-evolution of life and the geology, atmosphere, oceans, land. And we'll do that on Mars. As I mentioned once, Mars lost its magnetic field. It probably had problems keeping its atmosphere. Here's another Mercator projection where the reds and the whites are the tall areas, and the blues are the low areas. The blue area is where the oceans will be and the lakes, huge areas of water. And that makes the greens and the yellows the ancient shoreline. There's all kinds of information about this ancient shoreline. You know, we have another mission at Mars called the Mars Reconnaissance Orbiter, that if that chair sat on the surface of Mars, we could see it from orbit, okay? So we have this high-resolution camera, And so as we're taking high-resolution imaging of Mars, we can see all kinds of things that have happened in the past. We can tell that Mars has had tsunamis, where something has happened in the ocean, whether it's an impact of an asteroid or whether it's been a Marsquake of huge value, and the ocean has ran up these hills, grabbed these rocks, these huge boulders, and brought them down and laid them along the beach in a nice line. Okay? So it's those kind of things that our geologists on Earth are taking our knowledge of Earth and bringing it to Mars and understanding the history of Mars in some really exciting ways. The successful landed missions on Mars are shown here. And as you can see, those in black are no longer working. The two that are working are Perseverance and Curiosity. And they're huge. They're huge rovers. They're the size of an SUV, all right? And they're about a ton. Curiosity is 1 metric ton. Perseverance is more than a metric ton. And they're doing fantastic work because they are looking at the geology and chemistry and the mineralogy and determining many different important things. And so the secrets from Mars that we're revealing tell us, as we dig in the dirt, that red patina we see everywhere is only skin deep. And below that, we see gray Mars. We see surface material that is not unfamiliar to us. It's got carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Okay? That's everything between my two fingers in the soils. And it has nitrates, great fertilizer, and they're moist. So even though Mars lost a lot of water, it also has permeated the soils. And so there's a lot of water in the soils of Mars that we plan to use. Now that water is frozen, although the atmosphere, we can measure some humidity in the atmosphere. But the bulk of the water at Mars today is below the surface. There's kind of a frozen layer, it seems, at some level. And now we have some indication of some aquifers. So liquid water is flowing there. We can't find any life on the surface, but we do find indications of potential life that had existed on the surface. Microbial life. And that's one of the more recent discoveries that's really exciting. For us to be able to confirm that, we need to bring those samples back to Earth and really study them in our laboratory to then say, yea, verily, Mars had life in its past. If that is indeed the case, then there's no reason to think that there's life in the water aquifers below the surface. So over time, that also makes sense here on Earth. We had our astrobiologists look at life on Earth and measure its biomass. So that means all the humans and all the life, plant life, animal life, go into the ocean, take all the fish, and calculate the mass of life. Okay? Biomass. And then go below the surface looking for life. Go down in caves 2 miles below the surface, finding areas where there's water seeping and recognizing the microbial life all over the place down there and making an estimate of the life there. And what we find is there's more biomass of life below our feet than there is on the surface of this planet, plus the ocean. If you take that same basic principle of how we have co-evolved with this planet to Mars, and if Mars had ancient life on the surface, it's undoubtedly got life below the surface. When conditions get tough, life goes into the rocks. And so we're really excited about the opportunity of going to Mars and finding life. It's one of the reasons why scientists want to go to Mars. Finding life other than Earth life in another planet means that the concept of life being created in the galaxy is viable, and that means maybe there's all kinds of life out there and that we're not alone. And that, to most scientists, makes a lot of sense. And I think we're on the verge of some really tremendous discoveries, and that will happen in your lifetime. Well, when we landed on some of these beautiful vistas, they indeed do look Earth-like. This is Gale Crater from a perspective of Curiosity. So you just had Curiosity at a location, and then just spun around and took these images. What's on the other side of this crater wall, which looks like a mountain range, it's actually a crater wall, is the ancient ocean. And there's places in this crater wall that have been broken down, and the ancient ocean poured into Gale Crater. All right? So Gale Crater was full of water at one time. And that water interacted with the soils, well, with the Martian surface material, and changed the mineralogy, and we can measure that, and we can see that that has happened. And it has really been quite exciting to make many of these fabulous measurements. As we go now to the outer planets, these are much bigger. These are gas giants, Jupiter and Saturn, and we call Uranus and Neptune ice giants. And we call them slightly different than the gas giants, although they are giant-like planets that are mostly gas. It's the composition of the gas. And the fact that Uranus and Neptune have a different composition should have told us something happened way in the past that changed their composition from being like Jupiter and Saturn, dominated by hydrogen and helium gases, to having all kinds of ammonia and other types of molecules in those atmospheres. So something happened to those two planets that changed their composition. And we know what it is, and I'll tell you what it is. We'll reveal another secret. Well, Jupiter is an absolutely fabulous planet. This is data from the Juno satellite that orbits over the pole of Jupiter. And you can see its altitude as it comes down. And we do one fake thing here, and that is we go below the surface. We didn't really do that with Juno. Juno stayed above the surface. But we did that just for the ability to pop up at a different place and fly through the red spot. But we can see these cloud tops, and some of these cloud tops are higher than others. And that we can look at the strata, and we can understand then what some of the physics that's going on in these. Now we're coming out of the surface, and here's the big red spot, which is an enormous hurricane that's going on. How big is it? About 2 times the size of the Earth. All right? Now, Jupiter, once again, has 300 times the mass of the Earth and has really sucked material away that would have made our planets, Mars in particular, much bigger, and produced a planet that we would have called Super Earth, which is a terrestrial planet that's bigger than Earth. And in fact, super Earths were found around other stars. The most populous planet orbiting other stars is a super Earth. That's a planet we don't have in our solar system, all right? But we now understand how that can happen. It's in an orbit where it can accrete enough material to make that occur. Jupiter's got these wonderful satellites. These are the 4 Galilean satellites. We call them Galilean satellites because Galileo saw them with his telescope. Got in a whole heck of a lot of trouble. I don't know why, but he did. Io is as big as our own moon. So you can see these are pretty big objects. Ganymede is the largest moon in our solar system, and it is bigger than the planet Mercury, all right? Bigger than the planet Mercury. Now, you should be shocked if I told you all 4 of these moons were made at the same time. And the reason why you should be shocked is they don't look like the same, any of them, okay? You got Callisto, huge number of impacts. Got Ganymede with a few impacts, and then a lot of smooth surfaces. And you have Europa, where you can hardly find any impact craters. And Europa, Ganymede, and Callisto all have ice shells, all right? That surface is ice. And then you look at Io, has no ice shell. In fact, what Io's got, when we look at it in the infrared with Juno, is more than 100 active volcanoes going on all the time. You need a new Google map of Io every 88 years. That's what we estimate. It's turning itself inside out. Okay, why? It's lost its ice shell, all right? And so we know the energy that causes these moons to do this is because of Jupiter. They orbit in elliptical orbits, okay? To get to planets and to understand the motion of moons, it takes math, okay? Everything we've been talking about has an underlying mathematical framework, all right? And tidal forces mean that in an elliptical orbit, you're squeezed by the planet, all right? And Jupiter is massive. So Jupiter is squeezing the moon, pulling on the surfaces, all right, that are closer to it than further away from it on the other side. And these are big moons, so that pull can be easily measured. And then, if you're far away, you have a certain amount of the squishing. And if you go to the other side of your orbit where you're closer, you squish even more. And that heat has got to go somewhere. And on Io, it melts the rocks, creates the volcanoes. Europa is far enough away for which, as Jupiter goes through the squeezing motion every 3.5 days, okay, and that is heating up Europa, it melts the ice shell, but it's far enough away that the heat is not enough to dissipate the ice shell, and the heat produces water underneath the ice shell. And so Europa has an under ice shell ocean. We estimate there's at least twice the amount of water underneath that ice shell than there is on the surface of this Earth. Okay? And this moon is only about the size of our own moon. Okay, so that ocean is 100 kilometers deep. Okay? All these moons are tidally locked. All of them. All right? But life in an ocean, all right, if it starts, can hide in the dark areas, can swim in the light areas. And we know what the bottom of the ocean of Europa looks like. It looks like Io. So in the bottom of the ocean of Europa, we're going to get what we call here on Earth hydrothermal vents. So hydrothermal vents are going on. It's this lower picture on the right. We go to our own ocean and we see these hot areas where magma is heating the ocean, minerals come up, teeming with life. These were discovered in my lifetime, 1978, 72, 78, somewhere around in there, we started finding them. Now, we've been to 300 or 400 of these, and each and every one of them teeming with life. Didn't require one ray of light from the sun. That energy comes from the interior, and on Io, it comes from the tidal forces. That energy doesn't come from the sun, and that's true on Europa. So planets like Jupiter form a mini solar system where life can exist in ocean worlds. Now, Europa's got all the right stuff. It's got all the right material, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And we haven't measured exactly all of them, but we're pretty sure that most of that's there. It's got the energy from the hydrothermal vents. It's got a protective ice shell. And it's been that way for 4.5 billion years. Okay? And so there might even be complex life in the ocean of Europa. Enceladus is a moon of Saturn. Looks very much like Europa in many ways. And we see walls of water squirting out of cracks. Okay, and these walls of water are tidally forced from Saturn, producing energy that heats this ice shell moon, creating an ocean, and cracks in the ice allow this ocean to be sprayed into space. And we've flown through this with Cassini. Now, Cassini wasn't designed to be a life finder, but it's found some really exciting stuff, and there may even be life in the ocean in Enceladus. It, too, seems to have all the right stuff. Another moon, this moon is also the second largest moon in the solar system. It's called Titan. Titan is really fantastic. It has an atmosphere, and that atmosphere on the surface pressure is 2 times that of the Earth's pressure. So we're planning to drop a quadcopter into the atmosphere and have it land nicely on the surface, and then fly around making measurements at more than 30 places. Okay? And that mission is going to be launched late this decade, and it'll be in the early 30s when it gets there. And it will make some fantastic discoveries. Here's one of the things we wanted to look at. Now, this data I'm showing you coming from Cassini is from a radar, because Titan has a lot of clouds, although we can see aspects of its surface. The cloud cover makes it difficult to see everywhere. And so this radar penetrates the clouds, and it bounces off the surface, comes back up to the orbiter, and then we can analyze it. These are the kind of images we see. This is liquid. This is a lake on Titan. Titan is the only other body in the solar system that has liquid on the surface besides Earth. All right? Now, liquids are important because it's part of the life process. We bring in food, we bring in a liquid. For us, it's water. It is a solvent. We take the energy out of that material that we need for our body, and the waste is then eliminated with the water. That process is the metabolism process. And that's the top process for life. So NASA defines life as having metabolism, reproducing cells, and evolving. If we find those 3 things in an object, we're going to call it life. However, on Titan, this is not water. It's methane. So when Titan revealed this secret to us from Cassini, I decided at NASA headquarters, since I was running the planetary program, we needed to put some money into looking for what would life look like that wouldn't be carbon-based, that wouldn't be like us, that would use a solvent like methane, okay? And we call that whole discipline of looking for life not like us, weird life, okay? So we have a lot of scientists looking for weird life, and Titan is the place. And it's got an underground ocean. Uranus and Neptune, fabulous bodies. The Voyagers have been there. We've learned an enormous amount about them, and we're still making discoveries. JWST found a new moon and is observing rings like this around Uranus. Fabulous rings. Jupiter, we knew had a ring. Voyager made a couple images as it passed by Jupiter and looked back and saw a ring. And it looks like, Saturn, Jupiter, Uranus, and Neptune all have rings. Because that's indeed what Neptune has. Now, Uranus has got ocean worlds too. All right, same basic principle. And Neptune, with these fabulous rings, are being observed by JWST. And in fact, one of its moons, Triton, we think is a Pluto-like object. The astronomers decided in 2006 that Pluto wasn't a planet, right? How many of you think Pluto's still a planet? Yeah, okay, so there's a few of us. I don't know what's convinced the rest of you, but Triton is a Pluto-like object, all right? It's very different than our terrestrial planets. It's very different than a lot of these other moons. And it's made from debris left over in the outer part of our solar system. And there's a field of that material. And now we have seen at least 2,000 or 3,000 Pluto-like objects beyond Pluto. And we call this area the Kuiper Belt because it was originally proposed by Gerald Kuiper in the 50s. He said, hey, there should be a bunch of Pluto-like objects beyond Pluto in a debris field left over. And indeed, in 1990, we started finding them with telescopes good enough to see them, okay? And we know Triton is a captured Kuiper Belt object. So what's a Kuiper Belt object? Here it is. Here's the archetype Kuiper Belt object. It's called Pluto, and it has a moon, Charon. And it has, let me go back to this. This super spectacular, fabulous area. In fact, when we flew by Pluto with New Horizons, I don't think I could close my mouth for an hour. I was so smacked with this beautiful planet. Dwarf planet. And it has this heart structure, all right? Okay, this is a nitrogen glacier. These are snows. This red stuff is snows. There's only a few craters. This body is still evolving. It has an atmosphere. And this heart of nitrogen has all kinds of structure. It has highs and lows and troughs. We now know that these are tops of convection cells. What do I mean by that? If you boil, you boil water, the hot water goes to the top, cools, falls back down, creates this circulation. That's called convection, right, engineers? Convection, okay? Some heat source is below this, heating this nitrogen, creating these convection cells. They flow up, they form these areas, and they fall down in these troughs, all right? Fabulous. This thing is still an active world. And in fact, we can see that these nitrogen ices and methane ices, we can see it, there's areas that have got carbon monoxide snow on it. We find it has an atmosphere. Pluto was smaller than the moon and it has an atmosphere? Are you kidding me? Okay. It has frozen nitrogen lakes and it has volcanoes. Well, what comes out of the volcanoes? Water. It's what we call a cryovolcano. It spews, like in the United States, you'd go to a place called Yellowstone and see Old Faithful, all right? So these are spectacular structures, absolutely spectacular structures. And now we know, there's got to be something below the surface of Pluto. What we think it is a layer of water that's cooling. So the energy that's keeping this water liquid as it becomes frozen, that energy is heating what's above it, which is the nitrogen, and that heats the nitrogen and then moves it up and creates these convection cells in the heart of Pluto. And now we can look back and we can see there's life, perhaps, not like ours, walking on surfaces, but perhaps in oceans, in moons that orbit giant planets. And those secrets have now been revealed. Thank you very much. Somebody had to create the planets, right? So do we have time for some questions?
Yes.
All right, good. I have no idea what time it is. I lose track of time when I'm having fun.
Eu acho que vocês entenderam por que eu precisava trazer para vocês, né? A gente vai abrir para perguntas, os meninos vão passar os microfones, tá? Então vamos levantando a mão, a gente vai tentar ir pela ordem de quem chamou, mas como está bem lotado, isso pode ser um pouco confuso. Se tiver mais alguém da Aero Júnior aqui que pode ajudar passando o microfone, a gente pode passar 3 microfones de uma vez.
Okay.
Thank you, Jim.
Hello?
Yes, go ahead.
Yeah, here.
Yep,
Good afternoon, Dr. Green. It's an honor to have you here.
my pleasure.
My name is Mateus, and I would like to ask you, in your vision, is there any specific area or subjects of study that we can only achieve or exponentially progress if we work as humankind, not isolate institutes like the worldwide space agencies? Not like fusing them all, but cooperative work of NASA, ESA, JAXA, and Brazilian Space Agency, for example.
Yep.
Is there any area you think that could not be achieved with that?
Wonderful question, because I firmly believe that if we're going to make progress as a human race, understanding our place not only in the solar system, but in the galaxy, we have to work together. All cultures, all ideas, everyone should contribute. NASA's moving in that direction through what we call the Artemis Accords. Brazil is part of the Artemis Accords. That means you've signed up to work with us to explore not only the moon in the ways we talked about, but also going to Mars. We have more than 55 countries now that have signed up, and that's wonderful. The Apollo program, everything about Apollo was paid for by the citizens of the United States. And now we have more than 75 space agencies. 75 space agencies. All right? Okay? And now we're starting to work together. And that's really wonderful feeling. And we have wonderful examples of how well that works. And the prime one is the International Space Station. All right? Doesn't matter your background, doesn't matter what country you're from. You're an astronaut on a team, or cosmonaut, okay? On a team working together. That's just the way it's got to be if we're going to make progress. And you know, that next generation that's out here that I'm looking at, you're going to have to help make that happen. All right?
Thank you.
You're very welcome. Now, don't forget. Okay, good. You didn't forget. Okay.
Hi.
Yes.
Thank you. I'm a geologist, so I'm sorry about the question, but I wonder if you're studying something like tectonics on this, any planets or something that works like our tectonic plates here in Earth.
So didn't quite, you're a geologist?
Yeah.
Okay, so you're asking me a rocky question.
Yeah.
Okay, so there's 5,700 minerals on this earth, and 349 of them are made with dead life. All right? Now, we've been on Mars, and we can start looking at the mineralogy, and we've recognized minerals, and we have the same minerals here. Okay? And right now, we can identify about nearly 300 minerals, something like that. So we're nowhere near 5,000, all right? So we have a lot of work to do. But we've cored rock. We've cored it in areas where there was rivers flowing into the ancient ocean. We see chemical reactions that are occurring that are attributed here on Earth, because it looks exactly the same and has the same composition, as microbes eating material and interacting with the surroundings, all right? We see that on Mars, all right? So that stuff's been cored. We have a rock sample, and we need to bring them back. So right now, we're not done collecting all the rock samples we want. We have like 43 we're trying to do, and I think we're at number 30. But in a couple of years, we will have completed that. And now we got to go get them and bring them back and get them in the lab and get one in your lab. Or if you're a student, walk into Maria's lab and analyze the rocks and look at the mineralogy and tell us there's life or not there. Because as I said, there might be minerals that needed life to be generated.
Okay, James asked me to hand you, or whoever make the question, so if you can show them, just a little gift for him.
Yeah, everyone that asks a question gets a little gift. You know, when I talk to audiences, while you're getting to the next person, when I talk to audiences, particularly the public, I have a lot of kids that will come up to me, you know, come to the mic and say, well, what's your favorite planet? Okay. And so I hope at the end of today you already know what that is. Okay? Now, I have, as a head of planetary science for 12 years at NASA, funded more than 20 missions, okay? Virtually everything I talked about came from the missions I funded. And so when I get a question like that, and they know that I've been head of planetary, my answer to the question is, I love all my children equally. Now, that really annoys them. They don't understand that, but that's true. Every one of these missions has made exciting discoveries, you know, has revealed these secrets and more. I mean, I didn't even, you know, scratch the surface on most of this, and it's so exciting. We have a lot to learn. Okay, who's next?
So,
yeah.
Dr. Green.
Yes.
Let me preface this by saying it's a pleasure to have you here among
Oh,
us.
my pleasure. As I said, Maria invited me, you know, and I'm going to do what she tells me to do.
So it's a question I think is very relevant since we are here at the engineering school. But during the early days of NASA, NASA took a very hands-on approach with the engineering, along with the companies that were along the way. But gradually, with the years and the problems of engineering become more and more understood, it has moved on to think more about experiments and so on. And I'd like to ask, how is the situation now with the engineering within NASA, and how do you think the tendency is for the next few years?
So I think space engineering has an enormously bright future, because it's not now just a space agency, it's a ton of commercial companies, okay? You know, it's everything from SpaceX to Blue Origin, you know, to Voyager, to so many companies now are hiring fabulous engineers that are coming out, and they're developing new ideas and new systems. You know, landing rockets that we would throw away in the ocean so we can reuse them, not 1 or 2 times, 20 or 30 times, driving the cost of getting into space down is what's happening. Now, what does that do? Well, it enables us to move into an environment where we can have Normal people, I mean, you know, not a type A astronaut at the peak of their physical abilities going into space, but normal people going up into space and spending a weekend in a space hotel. That's our future, all right? Now, of course, they're normal people and they have normal problems and they may get sick, and so there will be space hospitals, all right? And in fact, the research that we're doing, not only on the International Space Station, but on other, that's being planned for some of these other commercial space stations, really tell us there might be a number or maybe a whole host of physical and biological problems people have that can be cured by going to a space hospital, spending a few weeks there, and then returning. Now, why do I say that? Because space provides an epigenetic environment unlike anything on Earth that open up genes that never fire in our bodies and produce new things. All right? Telomeres on your DNA get longer. Certain genes get expressed, which means they start becoming active that they wouldn't if they were on the ground. So that gives us a wonderful opportunity to do research in that area to uncover those things that can fix a variety of biological problems that humans and others have. So that whole field is just starting to explode. In your lifetime, there'll be space hotels and space hospitals. If there isn't, we've done something wrong. This species, we call the human race, cannot survive long without space. Trust me when I say that. Okay?
All right, thank you.
Sure. Now give him a, yeah, does he have the meatball? Okay, we call that the meatball, by the way. And I used to know why. Somebody coined that term. You know, that's the NASA logo, the nice blue NASA, and then a chevron and a bunch of stars and an orbit, you know, that was designed in the 60s, and somebody called it the meatball, and it really stuck. So anybody asks a question gets a meatball. Yes? Okay, so the question was, for those that didn't hear it, what about NASA's effort in searching for life beyond Earth? Have there been missions that do that? And the answer is yeah. Carl Sagan was a really big proponent, having two missions called Viking 1 and Viking 2 that landed, dug in the dirt, brought it in, and it had 3 life experiments. In each experiment, if each got positive results, we would say there were life there. But what happened is only one of the instruments gave positive results. The other 2 did not. So we didn't declare we found life. But the other problem was we didn't know what we were doing. Today, that would be the last place I would put the Vikings. There's far more interesting places to put the Vikings than there. It's like you land in the Gobi Desert and you don't find any life and you say, forget it, there's no life on this planet. What? Okay, so we could have picked a better place and we didn't give up. So one of the top things that NASA does is indeed look for life beyond Earth. And we're making tremendous progress in that. So I hope to come back in 2 years and tell you we found it. Okay? Yeah. We need a little time. Might be 3, but but we're hot on the trail.
Good afternoon, Mr. Jim.
Yes.
First of all, thanks to Maria Cecilia for this opportunity of being here. My question is a little simpler, I guess. what do you think about the possibility of the danger we can cause to another life forms in other planets like Mars? And also, what do you think about the danger the other life forms can cause to us? This possibility.
Yes. So you put your finger on an entire field of research, and it's called planetary protection. And it has guidelines. And we have agreed to those guidelines. Many countries that have space activities have agreed on using these guidelines. And these guidelines are that when we go to Mars, we're going to send as sterile a spacecraft as we possibly can make it, or at least as sterile as it needs to be based on where it's going. All right? So if it's going in an area where we think liquid water is, there's going to be, we're going to bake it. We're going to kill everything on it. All right? And then we're going to set it on the surface and let any biological entity that's on it from Earth die in the environment that it's in before we go where we need to go. You know, so we have all kinds of ideas on how to do that. Curiosity, I spent $25 million cleaning it to make sure there was no life on it, okay? And then we found this bug in a clean room that we had a heck of a time to kill. Everything we applied to kill the microbes, it ate, it grew. All right? That's how fascinating microbiology is. And it's called Pentabacilla thuroduoneuron, all right? Not that you needed to know that, but you know, that research goes on. You know, it's a wonderful set of research because we don't want to infect an area with our life because we're looking for life, and if we find life, we don't want to go to a place and say we found us there because we brought it, all right? We want to be able to say we found life that's there, all right? So that's one of the reasons why we do it. Now, also, when we bring these samples back from Mars, they're going to go into a BSL facility level 4. That's biosafety level 4, okay? That facility, we have many on Earth. Many countries are building those. And they do research in Ebola, in anthrax, in COVID, and SARS. All that kind of research are in these kind of laboratories. So we will isolate those samples, and then we'll test for pathogens. But I have to tell you, I'm not worried. I'd be happy to walk in there and lick that rock and say, okay, I didn't die. Here we go, give it up. Now, it's taken me a few years to feel that way. Why is that? Because I recognize the pathogens that kill us co-evolve with us. And even if life started on Mars and came to Earth, and we started out with the same ancestors, the evolution of that life and the evolution of life here will be so different that they will not be able to affect each other. That's an important thing to consider. And so I think okay, so I'm gonna speculate now. So we're gonna keep the cameras on. If the cameras on, I think we're gonna find life on Mars. I think there's been life on Mars, ancient life, and there may be life there now. And I think the life that's there now is in these aquifers, and because of the evolution of Mars, it is on its way out. And that the best thing can happen is for us to go there, find it. All right? Why do I say that? We are the only species on this earth that are concerned about the death of other species. Now, there are symbiotic relationships, but we really care, all right? We worry about being in a sixth extinction. We measure our past, and we've seen 5 massive extinctions that have occurred. We care about the planet. We care about life on this planet, whether it's plants or animals, and I think that's a wonderful aspect of us being humans, and we need to nurture that, and we need to take that philosophy with us for those that will live and work on Mars. And if we do find life on Mars that's alive today, not just ancient life, but is alive today, we're going to learn an enormous amount, not only about that life, but about ourselves, okay, and life in the universe. Okay, finding a second Genesis is a worldview change. It'll rock our world, I think, much like Copernicus saying, no, planets orbit the sun, they don't all orbit Earth, all right? And Galileo, you know, being in house arrest because he violated the church's thinking that the sun is a pure object, and he saw sunspots on it, and that all those things out there should be orbiting Earth, and they're not. There's a bunch of them orbiting Jupiter. Okay, all these worldview changes, okay, that have happened in the past, we're about ready for another big one, and I can't wait. Okay?
Good afternoon, Jim. I'm kind of nervous right now due to the utmost importance of this encounter here today. And I think I speak on behalf of everyone here. It's a pleasure to meet you. And I want to ask you, like, as an aerospace engineer that is willing to work with space technology, if you have any tips for us that are starting our lives in engineering world today, and if you know any way to work abroad, anything like this.
Yeah, I think when I was going to school, my PhD thesis advisor said, "Oh, you need to pick something and be an expert in it." You know, the phrase was "burn a hole in steel." All right, you know everything about this one thing. All right. And that when other scientists are having conferences and doing things and they want to learn about this, you're going to be invited, okay? So just specialize. Today, I think that's wrong. Today, I think the people that are going to be most successful are those that really understand various aspects of different fields, okay? And where they might fit in. We were just talking about this today. Aerospace engineer, or aeronautic engineer, those two are going to merge, I think. Space is an important element. Let me give you an example. We're flying a helicopter on Mars right now, all right? We're going to drop a quadcopter on Titan, all right? Okay? Charles Lindbergh, in 1930, crossed the Atlantic, built a fabulous plane, which was mostly gas, all right, and crossed the Atlantic in 33 hours, and many people in the papers hailed him as that's just such a magnificent, wonderful thing, and then the detractors say, well, why would you want to go to Europe in 33 hours? I can take a boat and be there in 7 days, all right, you know, and now we have to be there in 7 hours, all right. We just launched a few years ago, and then this is now a couple launches, of people, normal humans, not top-level astronauts in the peak of their physical abilities, in capsules that have orbited the Earth, okay? Okay, and one orbit is 90 minutes long. Detractors say, wow, why is that important? You've got to be able to think about how the aviation industry is going to change. I want to be able to get into a rocket, launch from Washington, D.C., orbit the Earth, and land in Tokyo in 50 minutes, and even go the long way around, okay? Not taking the short route, I'll go the long way around. 50 minutes. The ability of space to completely open up the globe in that way is now available to us, all right? And we're seeing more and more of those things. As they make travel into space cheaper, space has got to be folded into our environment. And aeronautics is going to be incredibly important as you marry it with a lot of the aerospace technologies. That's my opinion. Okay?
Good afternoon.
Where are you at?
Good afternoon, Ms. Dr. Green. I hope you are having a great day.
I am.
So I do have a question. With increasing automation and AI, with your in space missions, do you believe future interplanetary exploration will become fully autonomous, or human decisions still be crucial in real time?
Yeah, really good question in the sense that there's been a number of science fiction movies. Now, I like science fiction. I don't just gobble it up and read it, but I do enjoy a lot of science fiction, particularly movies. I leave my science at the door, and I go in and I really enjoy what's going on, whether it's physically correct or not. But there's a number of themes that come out that I think are very important and will be true. All right? Did you watch 2001, Space Odyssey, where the AI system, HAL, seemed to go berserk and kill all the bags of water? Okay, killed all the humans. All right? Because they compromised the mission. Why? Because the mission was to find life. The humans were looking for life like them, and Hal was looking for life like it, and it found it. The life that they saw was artificial intelligence created by another civilization somewhere, in the universe, and leaving a calling card in our solar system. And so the humans would jeopardize that mission, which is why Hal got rid of them, because they didn't need them. And the life they found was artificial life. That, to me, makes a lot. I realized that when New Horizons was leaving Pluto on its way out into the area of the stars, because I realized that's what we're going to be doing ourselves. We're going to be sending satellites that have tons of artificial intelligence on it to be able to go work, live in extreme environments, and go visit places we can't physically go to. That'll be the first thing we do. And I think if there's intelligent life, that's what they would be doing to us. All right? And so what we're doing now in looking at life on other planets is looking for a variety of technologies that these planets may have. And we call those technosignatures. And that will include traces of things like artificial intelligence, very large space structures, and chemicals in the environment that aren't natural. I mean, just a ton of things we're looking for that indicate that there's intelligence of life on those planets. So those are the things. Oh, thank you. I can have done that. Well, thank you very much. Those are the kind of things that we're doing now. And I think we're going to see some fabulous results out of that in the next several years. So yeah, artificial intelligence is really important, and it's going to be at the forefront of what we do as we explore deeper and deeper into space.
Thank you.
Hi, Jim. First of all, thank you for the lecture. It was really good. Thank you for you here.
You're very welcome.
And I'm more from the mining area, and I want to ask you, because you show us that it's possible we have things working on space, and we can also chase for human being capable to stay out of the Earth. So do you think that in that life, we all here maybe can see something like space mining in the moon or asteroids and something like that? And if you think that, like in a few years, that is gonna change from the fiction to the reality?
Space mining is going to be really important. That's what's going to help commercial companies come with the scientists that want to look at these planets and understand their origin and evolution and the resources that are there and how they got there. And then what will come along is being able to extract those resources that will allow humans to be able to live and work in these remote places. I think that's a huge area. I mean, it's another enormous opportunity. So yes, space mining, I love it.
Thank you.
Hi, so I want to ask you about dark energy because we have little to no information about that, but it fills 70% of our universe. So I wish to know, I want to know like what your theory about it, what you think about it.
Yeah, dark energy and dark matter, okay? So those are two concepts that explain things that we don't really have a good feeling as to what may really be happening. The term dark matter occurred in a paper by Zwicky in the 30s when he was looking at galaxies, one particular galaxy and how it moves, and recognizing that it doesn't have the matter it needed to move the way it's moving. It actually should be flying apart. Well, if it's not flying apart, gravity is holding it together, and you look at all the gravity sources, there's not enough gravity to keep it together, so there must be some missing matter, some matter I can't see. And if I can't see it, I call it dark matter. Now it turns out that was just a lone thing, and nobody did anything for decades. And now you get into the 80s and 90s when astronomers are really taking those basic ideas and recognizing, my goodness, they're right. There's an enormous amount of matter that's missing, and we can't see it. Why don't we see it? Matter interacts with light. Your matter, light bounces off you. I see you because of your interaction with light, okay? But dark matter doesn't interact with light. It only interacts with other masses. It only interacts through gravity. So electromagnetic waves pass right through it. That is so strange, and yet it's a huge part of the universe, and so astronomers are on the hook to find it. Dark matter pulls things together, but when we look at certain objects, like clusters of galaxies that are coming together, the different clusters are flying apart. And so there's some sort of energy pushing them away. And so we call that, because we don't understand it, dark energy. All right? So right now, keeping the universe together is dark matter. Keeping the universe from flying apart is dark energy. And there's a fight between the two of them going on. Are we going to end up being just thrown into the nothingness and everything just keeps moving away from us? Or is the whole universe going to come together, collapse, explode, and start all over again? All right? We don't know yet. Stay tuned.
Good afternoon, Jean. Thank you very much for being here.
Sure.
I'm delighted to be here with you.
Oh,
Thank you very much for coming to talk with us. So thinking about all this that you told us, about all those patterns that you look through universe, and all those planets and everything, like how all those things can tell us about the beginning. So for sure, as you wonder yourselves about how our patterns in solar system tell us about other systems, for sure you ask yourselves how this tells us about the beginning, not only of life, but the first creation of universe.
Yes, that whole topic, the creation of the universe. The theory that seems to work the best is called the Big Bang theory, okay? In other words, it starts with one equation. Once again, it begins with math, okay? And that equation Einstein came up with, and it is E equals mc squared, all right? Very simple equation, unbelievably powerful. You look at it. On one side is energy. On the other side is mass, and c is a constant, okay? Speed of light. That means energy can be converted into mass, and mass can be converted into energy. So let's start the universe with only energy. And something happens in a vacuum that is full of energy, and it begins to produce mass. And those initial things that it produced that have mass, we call quarks. And those quarks combine into other things, and we call those protons and neutrons and electrons. And those protons, neutrons, and electrons combine into other things, and we call that atoms, where you have a nucleus and you have electrons orbiting, and those atoms get together, and we call those molecules. And so all that progression of things starts with an event of energy being converted into matter. And that event is called the Big Bang. And although it's not really a bang, it's an event. But the term is really stuck, and it's called the Big Bang. So now, thinking of things that way, we can look back in time by looking in space with the most powerful telescopes, looking for events that have occurred in the past that are now very far away, that have given out light, and that light has come to us, and because it's moving, it's Doppler shifted, and it's in various frequency ranges. And the most important one right now is in the infrared, and that's where JWST is. So JWST is looking for the first galaxies that are made. Okay? And that means you have to make the first stars. And the first stars are made by the first set of atoms. So we're getting close to going back, but we have to use these kind of things to do that. And so if you follow what JWST is doing, it's doing fantastic things. It's telling us galaxies were made actually pretty quick, far faster than we ever imagined. First 200 million years, the universe is making galaxies. What is that all about? Okay?
Thank you very much.
Firstly, good afternoon.
Okay, yes.
I have a question. You cited a lot of places where we may find life in your lecture. And, sorry, I'm a bit nervous. And I wanted to ask, which one do you think is the most probable? And also, in the case we actually find life in the solar system, how that would change our approach to space exploration and the conflicts it would generate.
Yeah.
Thank you.
So personally, I think we have a good chance of finding life in the ocean of these ocean worlds. And the one I think that's got the top one on my list is Europa. I think it may even have complex life. We don't know that because we haven't gotten the ocean. So NASA, so in 2006, when I became head of planetary, I started investing in submarines, okay? It's not just spaceships. Spaceships get us where we need to go, and our robotic systems are rolling on the surface, but not everything is a hard surface. There's some icy stuff, and we want to get under the ice, and we want to get in the water. And so we started developing a variety of submarines. And then we used those on Earth, and we tested all kinds of things to see how easy it is to get submarines in these ocean worlds. So we're making enormous progress in those areas. I think life has been on Mars. There's indications of that. It's not for sure. It needs still to be proved. But the more we do, the more we see that that's a good possibility. Explains a lot of stuff. It's harder to explain away all the things that life does by non-life things, and things just sort of accumulate. So I think we've got several locations that in the next couple decades we'll be able to determine it has life or had life. And that will be really eye-opening for us. It will really, I think, tell us about what's going on in the rest of the universe. To make those measurements happen, we will have to come to grips with planetary protection. We will have to come to grips with how we interact with that life or whether we don't interact with the life. Carl Sagan said, if we find life on Mars, we should leave it to the Martian. Okay, leave Mars to the Martians. And I disagree. I think we can learn to work together. And I think that will be beneficial for both our life and that life, because we are a species that is concerned about other life. But we can't just go into these things blindly. We have a lot of work to do, a lot of research to do, to be able to determine what the right thing to do is. Okay? I hope that answered your question. If you take pics, please post
A
them.
gente vai ter tempo. Sorry, Jim.
Well, I was just going to say once again, I'm delighted you're taking pictures. Please post them. The more you talk about some of the fantastic things that are going on in the university and in the universe,
Inclusive, marquem a Escola de Engenharia, UDA e a Aero Júnior na foto de vocês, para a gente poder repostar. Nós teremos tempo para mais 3 perguntas, mas se puder, não sai correndo ainda não, porque a gente quer tirar uma foto com todo mundo. Tá? Então, a gente vai ter mais 3 perguntas, tira a foto.
Here.
Yeah, go for it.
My question is about Mars, and I want to ask you, sorry, I'm nervous. It's about the travel to Mars. What did you think about the human fact? Because we know that in space station, when we come back to Earth, we have a lot of consequences. And I want to know what is your opinion about this when we go into Mars.
Yeah, this is a really tough problem, okay? And we've known about the problems associated with space travel for quite some time. And we've even tested on the International Space Station a couple things. We took twin astronauts, okay, identical twin astronauts, the Kelly brothers, Scott Kelly and Mike Kelly. We left one on the ground, and we took Scott Kelly up on the International Space Station, and he stayed for nearly a year, which would be what the trip would be to Mars. And then we brought him back, and then we compared the two, and all kinds of things changed. The epigenetics, which means the environment of your cells and the environment of your DNA, is so different that your genes, some become active, some don't become active. There's all kinds of problems with different types of cells in your body. Some are fine, some go through big changes. And now we're faced with the reality that, okay, we're going to be traveling to Mars. These changes will occur. What are the big problems? What do we need to do? What are the medicines? What are the mitigating factors or the strategies? And we're coming up with them. But I have to tell you, I think we'll whip all that. The biggest problem we're going to have is psychological. Okay? Now we're going to, for who's in the social sciences? Everything's connected, by the way. Our biggest problem is going to be boredom, being in a can with your 5 other best friends, and if they're not your best friends, that's going to be miserable too. Being away from home, Okay, there's no cats in space. That's for you, Maria. She loves cats. And you know, how are you going to survive? We looked at what happens in Antarctica, where people winter over in an extremely cold environment, where you can't get in and you're not going to go out. You're trapped. And it is freezing cold, and you've got to work together to survive. And the end result is then applied to space. So for a crew of 6 going to Mars, there's an 89% probability that one of the 6 will have behavioral problems, will be psychologically depressed, maybe even suicidal. I mean, there's nothing more disastrous than that to ruin a mission than to have another astronaut going berserk. Or stir crazy, as we might call it. So we have to work these issues. And at ISU, where I met Maria, we did a team project where we had students looking at how to use the metaverse in space applications. So if you've ever put on a virtual reality system and played a game where you're either killing dragons or running around from one level to another, or castles, it really lights up different parts of your mind. That framework can be used like the holodeck on Star Trek. We can do that right now. Okay? There's 5 hospitals in the United States that's doing research in virtual reality to combat depression. And they're coming up with new ways to do that. That's fantastic. So the computer nerds that are developing games in virtual reality are helping everybody from with PTSD to depression and suicidal thoughts, to then even making space travel happen. These things are related. This is why if you focus in one area and do nothing but that and ignore everything else, you're going to ignore the opportunities of applications that you never thought of possible. Okay? I think that's a huge thing. I think that's just going to be, that's where a main battle is going on, and how we're going to handle the psychological problems of going to Mars. Now, Mars will afford us the opportunity of being in a new environment and with a lot of new challenges. And those challenges will be in the daily basis. And therefore, you'll have a lot of variety, and that'll be good. But if you have somebody that gets depressed, they don't do their jobs, or they don't do them right, then somebody else in the crew is going to have to do it, and all of a sudden now you have resentment. You just have a whole cascade of different problems that occur. And so we have to work those out. And so there's plenty of things to research in those areas. So if you like that area, the International Space University did a wonderful report on that, and that report is on their website, and you can read it and learn about how to use the metaverse to battle depression in space and use it for other space applications. So for the computer scientists, computer engineers that are engineering games, you got a space future. Okay?
Hello. First of all, thank you for coming to our university, for your time, and Sarah. When you talked about Mars, you said that maybe it has sustained life in the past, but due to climate changes, rapid climate changes, it has gone. Is there any possibility that it's going to happen on Earth as well, like if the climate changes keep happening the way they are right now?
Yes. What's happened on Venus can happen on Earth. What's happened on Mars can happen on Earth. This is why we do comparative planetology, to understand where these planets are in their evolutionary state, because they are at a different location than the Earth. from the sun. In 800 million years, we will receive as much light as Venus does. And our atmosphere will be very much like Venus, and it will be too hot, and it will be, we wouldn't be able to live on the surface, and we know that, okay? That's what Venus tells us. I'll give you another couple really important examples. Why we know about climate change is because of the Venus scientists, okay? They took that huge atmosphere with carbon dioxide and they brought their codes to the Earth and they ran simulations by just adding a little CO2, and all of a sudden they get more and more of a Venus-like environment, okay? Now, when you think about this, it actually sounds a little crazy. Okay, why do I say that? Well, how much CO2 is really in our air, okay? We measure it in parts per million, all right? So right now there's like 425 parts per million. Well, that sounds awful small. 425 parts per million? What are we worried about? Can we double it and triple it? Okay? You know? And yeah, we could. That may happen. But it's how that affects the rest of the environment. Now, what do I mean by that? CO2 is a greenhouse gas. It allows light from the sun in a very large spectrum to come in, heat the ground. When you heat the ground, you change that energy into the infrared, and then the ground radiates in the infrared, but the CO2 loves the infrared and stops it from leaving. So then the infrared light just builds up in intensity, and that, of course, is what we call heat. And so it just gets hotter and hotter and hotter. It's very similar to what happens in your cars during the summer. Okay, you're just about ready to experience this. You know, you keep your car shut, it's out in the sun all day, you get in the car, man, is it hot. That's because light comes in through your windows, which is opaque, heats your upholstery, then the upholstery emits infrared, but the infrared doesn't see a clear windshield, it sees a dark shield, and so it doesn't leave, and it just sits and builds up in the car. Okay? So these modelers took that, brought it to Earth, and started adding the CO2, and what happens? CO2 is not the most important greenhouse gas. What? Okay. What's the most important greenhouse gas? What is the gas that changes the heat of a planet rapidly? Do you know what it is? It's water vapor. Okay? That's the top greenhouse gas. Well, we're not going to get rid of the water. All right? So what's the next one? It's CO2. What's the next one? It's methane. Now, methane doesn't last very long in the atmosphere. It can be broken down, but when it gets broken down, you end up with more CO2. But just imagine changing the heat on this planet causes what? The ocean to rise, more humidity, more heat. So our biggest problem is water vapor. And so some of these triggers where you can actually add just a little bit of heat to the situation, like the greenhouse gas of CO2 is, really has an overall global effect. So we have to know all those things. We learned that by those climate scientists going from Venus to Earth. That's why we know. The concept of climate change comes from NASA, all right? What about the ozone hole? You know, we're living in a world where we're protected at 20 kilometers above us by a molecule called O3, so you got 3 oxygens that are hanging together, and what does it do? It loves to eat ultraviolet rays from the sun. Without that, that ultraviolet light comes down, you get skin cancer. Plants hate it, they die. You start killing off the phytoplankton in the ocean, which is at the bottom of the food source for all fish, all the way up to whales. If you don't have phytoplankton, you're not going to have whales at the end. You know, so all these things that are related like that, now we find in the 80s this big hole coming out in the ozone, all right? And we realized what it was. How did we find out? Because we found chlorine destroying ozone on Venus. And I think Carl Sagan was one of the authors of some of these papers that were doing that. And so we recognized, hey, we ought to be looking at what chlorine we're generating on this planet that goes up and destroys the ozone, okay? And we found out it's CFCs, which is a chemical we produce, chlorofluorocarbon, and so that means there's chlorine we generate like crazy, and it destroys the ozone. So we then came up with an alternate, and we did it globally. We got together. Think of this. We actually got together globally and stopped the production, all right? And found alternate sources. And that happened because of planetary scientists comparing what was going on one planet to our planet. We are so lucky to have a Mars and a Venus in our environment to see these bookends and understand what we're going to evolve to over time. They've really helped us out enormously. And that's because all this stuff is connected.
Gente, a gente tem que esvaziar o auditório para o pessoal que cedeu o auditório para a gente. Então, a gente, infelizmente, vai ter que encerrar aqui. Eu gostaria de pedir aí um aplauso de agradecimento para o Jim.
Well, thank you very much. Thank you. Thank you. Thank you. Thank you very much. Thank you. Thank you. Thank you. Thank you. Yeah, it's a real honor to be here. I really enjoyed our time. And to me, it went very fast. I don't know. Hopefully, it went very fast for you. Thank you very much.
We are taking a picture now. The director suggested a picture from there. And so I ask everybody to stay up so we can come here and take a picture with all of you. Gente, espera a foto. Tô pedindo nada para você, só uma foto.
Tô só coordenando aqui. Animação, gente. Grita mais alto que sai na foto.